So today we're going to continue using the chain theorem in order to figure out the derivatives and integrals of some special functions, in particular logs and exponential functions. After today, we'll pretty much know how to compute the derivatives of most functions that you're likely to encounter. Now you may have noticed when taking derivatives that up until this point, if we took the derivative of an algebraic function, we got an algebraic function. If we took the derivative of a polynomial, we got a polynomial. The derivative of a rational function was rational. Also, the derivatives of transcendental functions were transcendental. The derivative of a trig function, sine of x, was another trig function. Same for the other trig functions. When we took the derivative of e to the x, well, what did we get back out? Just e to the x. So, for the most part, functions have kind of kept to themselves. But today we're going to learn how using derivatives we actually can mix functions together. So here we have a theorem that tells us how to take the derivative of something involving the natural log function. So the basic form says that the derivative of the natural log of x is going to be equal to 1 over x as long as x is greater than 0. And below it here what we have is the chain rule version of them that we'll talk about in a second. So to think about why the first one is true, what we can do is we can say, well, let's consider the function y equals the natural log of x. We want to find the derivative dy dx, so we would want to find the derivative of the natural log of x. The problem is that's exactly what we want to find. So instead what we do instead is we think about, well, we know what this means. Y equals the natural log of x is the same thing as saying e to the y is equal to x. And now we can take the derivative of both sides. So we take the derivative of both sides of this function. And on the left-hand side, well, the left-hand side is a little tough, but it's not so bad. It's just a chain rule. So what we have is we have the derivative of our outside function e will just be e, and we leave that inside function alone. And now we need to multiply by the derivative of y with respect to x. So this is definitely a chain rule here. And this will equal, well, the derivative of x with respect to x is just 1. And now if we solve this, what we have is we have the derivative of y with respect to x, which we wanted, is going to be 1 over e to the y, which we can write as 1 over x. Remember, way back up here we said that e to the y is x, so this is why we can replace our e to the y with x. So now we have that the derivative of the natural log of x is equal to just 1 over x, and that was our theorem. So let's go ahead and try to use this to compute some derivatives. So let's start by taking the derivative of the natural log of 3x. So in this case, the natural log is our outside function, and we have 3x as our inside function. So when we take the derivative here, well, we have to think about taking the derivative of our outside function and leaving the insides alone. So this says we need to take 1 over, and we need to leave that 3x inside. So this is the derivative of our outer function. And now we need to multiply by the derivative of our inside function, which is 3x. And hopefully you recognize that this is the exact form given in property 2 up here of how this will work with the chain rule. Our inside function, u of x, was 3x. And so that's why we have u prime and the derivative of 3x. And the 1 over part comes from the derivative of natural log. And so to complete this problem, we just work through the computation. This is 1 over 3x times the derivative of 3x is just 3. And for those who like to simplify in the room, this is 3 over 3x, which is equal to 1 over x. Now that might be a little surprising, but let's think about why this is true. Well, remember, we have certain properties of logarithms. And one of the properties of logarithms is that we can write this as the natural log of 3 plus the natural log of x. That is, when we multiply things, they come out as addition. And now, what happens if you take the derivative of the natural log of 3 plus the natural log of x? Well, this first part is just going to be a constant, so the first part becomes 0. And then we're going to add on to this the derivative of the natural log of x, which is 1 over x. So we just get 1 over x. This is very common when you have logarithms. You always want to kind of rewrite first if you can, because it can save you a lot of work. Logarithms are awesome, and they save a lot of time and energy. But overall, this is two different ways to take the derivatives. So let's try to take the derivative of this function. I encourage you to pause the video, try it yourself before seeing how it's done. So hopefully you looked at this and you said, ugh, there's a quotient inside my logarithm, but that's not a big deal because I can break this up using subtraction. And then this first part isn't so bad because I can bring that exponent down in front. And so now I have a much nicer quantity to take the derivative of. I need to now take the derivative of 3 times the natural log of x minus the natural log of cosine of x. And the first part isn't so bad. The constant just hangs around. 3 times 1 over x. It's a very simple derivative. For the second part, it's a little bit more work. We have to recognize that this is a composition. Natural log is our outside function. Cosine is our inside function. So when we take the derivative, we're going to get 1 over, leaving the inside function alone. And we multiply by the derivative now of cosine because of the chain theorem. So overall, we end up with 3 over x minus negative sine of x all over cosine of x. And for those who love simplifying, 3 over x plus tangent of x. Overall, though, not so bad as long as we remember to use properties of logarithms to simplify first. That way we don't have to do a quotient rule in there. So we'll do one more example before we move on to other ideas. So let's try to take the derivative of the natural log of sine of x plus 5x. Now in this case, there's nothing we can simplify first. We have this addition in here, so that's not one of our properties of logs that make this any easier. We just have to go for it. So let's take the derivative of the natural log of sine of x plus 5x. And so now I've written my inside function. It's still a composition. We've still got natural log on the outside. But now my inside function is a little more complicated. But overall, when I take the derivative, it's the same basic process. It's going to be 1 over, leave the inside stuff alone, multiply by the derivative of the inside stuff, cosine of x plus 5. So it's the same basic process always when using logarithms and the chain theorem. It's just it takes a little different form in terms of this leaving the inside stuff alone part. Now one of the things we notice about the natural log function is it can only take positive values in. So often what happens is we want to use the natural log of the absolute value of x. So we also need to figure out how to take its derivative. And as it turns out, the absolute value doesn't add a lot of complications to the derivative. In this case, the derivative of the natural log of the absolute value of x is still 1 over x. But one of the nice things it tells us, because integrals and derivatives are practically inverses, is that we can take the integral of 1 over x dx and end up with the natural log of the absolute value of x plus c. And we also get the chain rule version down below. The derivative of the natural log of the absolute value of some function will be equal to the derivative of that function all over the original function. As always, let's see this in an example. So suppose you have this function w of t is equal to the natural log of the absolute value of 5t squared. Well, we're not going to bother simplifying here. We're just going to go for it and take the derivative. So let's take the derivative with respect to t of the natural log of the absolute value of 5t squared. So our natural log function is still our outside function. 5t squared is inside. And using the properties, what we know is we know that this is going to be 1 over, leave the inside function alone, and in this case, we drop the absolute value signs, and we multiply it by the derivative of the inside there. So the derivative of this in this case will be 10 times t, because we bring the 2 down using the power rule. So overall here, what do we end up with? Let's see. So it's 10t over 5t squared, and after some canceling, we just end up with 2 over t. And that's it. That's all there is to taking the derivatives. It's just remembering to use the chain theorem carefully each time. Now, for better or for worse, not everyone likes e. Not everyone is willing to write their exponential functions with e as the base. So we have to learn how to take derivatives when we don't have e as the base. So for example here, we've seen this before. Let p of t equal 2 to the t measure the number of cells in a dish where the cell splits every hour and t is measured in hours. So as this goes on, this will tell us what our current population is. But now we can ask the derivative question, which says, how fast is this population changing? But before we can take the derivative, we need a couple definitions. Our first definition is that if a is a positive real number and x is any real number, then we can define this new function called the exponential function to the base a. We'll write it as a to the x, but by definition, what it means is to compute this thing, you need to take e to the natural log of a to the x. Little note, if a equals 1, then y equals 1 to the x equals 1 is a constant function. So it's a little boring if your base is 1. But anyways, what does this really mean? What this means is if you write 2 to the third, what you're really saying is e to the natural log of 2 times 3. So this means our function 2 to the t is really e to the natural log of 2 times t. So that's what it really means when you say this, and that's really how we're going to compute them in order to compute the derivatives. In a very similar way, what we can do is we can define logarithms with other bases in terms of the natural logarithm. So if a is any positive number and x is any positive real number, then the logarithmic function to the base a is denoted by log base a of x and is defined by this equation here. So to compute the log base a of x, we write the natural log of x times 1 over the natural log of a. So you may have actually seen this called in some places the change of base formula. That is definitely a B, I swear it is. And so this was how you computed other bases. So the idea here is that, for instance, suppose you want to compute log base 3 of 7. Well, you don't have log base 3 on your calculator. So what you need to do is you need to take the natural log of 7 divided by the natural log of 3 in this case. So you take the natural log of your input divided by the natural log of your base. Whatever number that is, that gets you the same logarithm. So now this is nice though, because using this idea we can now compute derivatives, because we can compute the derivative of e to any function. We can compute the derivatives of natural logs. So here we have the formulas for how to compute derivatives for bases other than e. So if a is a positive real number, what we can do is we can compute the derivative of a to the x, this exponential function, is just going to be the natural log of a times a to the x. So let's talk about this. Well, the derivative of a to the x is going to equal the same thing as the derivative of e to the natural log of a times x, because this is how we defined it. But this right here is just a nice composition of functions, so our chain theorem works. E to the something is our outside function. Natural log of a to the x is our inside function. So when we take the derivatives, what we have is we're just going to have e, leave that inside function alone, multiply by the derivative of the inside function. And well, what does this end up being? This is just going to be e to the natural log of a times x. And what's the derivative of this going to be? Well, the things to notice are that natural log of a is a constant times x, so we're just left with natural log of a. And what we can do is we can now simplify this, because again, e to the natural log of a to the x is just a to the x times the natural log of a. And then, of course, it's traditional to move the constant in front of the rest of the function, so this is how we get our derivative formula out. Very similar things apply to the other formulas. So 1 and 3 are the very important ones to know, and 2 and 4 are just the chain theorem versions of them. They tell you what to do in terms of composition. But let's do a few examples just to make sure this makes sense. So let's start with our friend the cell doubling formula. Well, there's two ways we can proceed by this. One way is we can memorize the formula and use it. So the way I'm thinking most people might want to do this is they might say, well, if I need to take the derivative with respect to t of 2 to the t, by my formula, this will be the natural log of 2 times 2 to the t, since in this case, a is equal to 2. The other way to do it is to have to work through all the details every single time. So the derivative of 2 to the t is equal to, well, I know by my change formula that this is e to the natural log of 2 to the t, and this, I know via the chain rule, is going to be e to the natural log of 2 times t times the natural log of 2, which I know is just 2 to the t times the natural log of 2. So you can just memorize them, or what you can do is you can work through them every single time if you want to. It's totally up to you. I might advise memorizing them. So now let's look at an example that involves the chain theorem. So in this case, what we have is we have our outside function is 2, and the inside function is cosine of x in this composition. So now when I take the derivatives, I'm going to want to follow the chain theorem version. So the chain theorem version says it's the same as always. You take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. So now when we take the derivative of 2 to the cosine of x, what we end up with is, well, the outside says we have the natural log of 2 times 2 to the keep that inside function the same, multiplied by the derivative of the inside function. And so when we simplify, we have the natural log of 2 times 2 to the cosine of x times the negative sine of x. So not so bad, it's just a matter of thinking through what the form of the derivative of the outside function, keeping the inside the same, is going to be. We'll do one more example here. So this looks like fun. We've got logarithms to different bases. We've got an inside function here in our composition that's a quotient. Oh my goodness, lots of fun stuff. But we want to think about what should we always do when we're faced with logarithms first. That's right, our old buddy rewrite is back again. Rewrite says the first thing you want to do is you want to break this up. So we can write this as the log base 10 of t squared minus the log base 10 of t squared plus 3 all to the fourth. Those exponents are going to come down in front, so this ends up being 2 times the log base 10 of t minus 4 times the log base 10 of t squared plus 3. And now that's about as much as we can do. This plus here stops us from breaking up the log anymore, because we can only break up multiplication, division, and exponents. And that t is about as simple as it gets. So now we're at the point where we need to take the derivatives of each of these parts. So this means now we can compute the derivative of this function by computing the derivative of these easier looking parts. So the first part here, the derivative will just be 2 because it's a constant, it stays around. And now to compute the derivative of the log base 10 of t, we need to go up here and use rule 3, which says this will be 1 over the natural log of our base times t minus now 4. Now in the second part, we have to follow the chain theorem version for logarithms, but it's not so bad. This will be 4 times 1 over the natural log of 10. Keep that inside function alone, don't touch it. Multiply by the derivative of the inside function, 2t plus 0. So again, always when we add these new rules, it's always just a matter of remembering the chain rule version is pretty similar. We just got to keep that inside function the same and multiply by its derivative. So overall, not too bad. A few quick notes before you try the problems for yourselves, try the video quiz, and post a question. On page 160 of the book is this summary of all derivative properties that we have learned. You can pretty much take the derivative of almost any differentiable function you're going to come across in your entire life now. There are some weird functions out there to take the derivatives of, but it's very unlikely you'll encounter them, and if you do, there's going to be other ways for you to get around that problem. Now, please memorize the properties in words, not just the symbols. It's very hard to get the symbols right if you don't understand the properties in words, okay? Memorize them as sentences. Write out the properties as sentences and memorize those. It's much easier for people to keep sentences in their head than it is to keep symbols in their head, okay? So what I want you to think about is it easier to keep track of a story, or is it easier to spell supercalifragilisticexpialidocious, okay? We can say it. It's good in our heads, but there's no way you can memorize the symbols to spell it out. The way I also remember this is thinking about that pushing symbols around the page does not help, okay? We don't want to just memorize patterns that move around. You really want to memorize the words and ideas behind them. So symbols is very important. Don't just push them around the page.